Good evening, everyone. Yesterday we talked about the physics of the sun, the star where, with which we are living together. Today I'm going to concentrate more on Aditya-L1, what kind of experiments and expectations we have from this particular mission. The background picture, again, we explained yesterday that you have the sun, which is the source of the particles and radiations coming in the interplanetary medium. The interplanetary medium is the medium between the sun and the other planets. And the gray lined ones are the magnetic field lines, which are coming from the sun. And they are in a curling fashion because of the solar rotations, which tracks the magnetic field in the interplanetary medium. And the events which happens on the sun, like solar flares and coronal mass ejections, as well as the solar wind, creates the plasma environment as well as the magnetic field environments, which are dynamic in the interplanetary medium between sun and the Earth. I should say that we have a satellite at L1 point, which is the Lagrange one point between sun and the Earth. And it's about 1% distance from the Earth, 1% of the Sun-Earth distance from the Earth. So we'll talk about the details of Aditya payload and some of the preliminary observations from Aditya. Now, this interplanetary medium, as I said yesterday, we have the particles and radiations. These two are the information carrier from any of the source, especially for the sun. And particles, we said these are the charged particles, electrons, protons, and heavier nuclei, and also neutrons. And radiations, which is mostly electromagnetic radiations, and we do photometry, spectroscopy, and polarimetry. Okay, so these two we discussed it yesterday in the general sense, and these two are the typical measurements which is done in any of the missions related to astronomy and planetary measurements. And what I have listed here is some kind of instruments which are used to do the measurements. For example, the remote sensing measurements includes imagers. Imagers means you do a two-dimensional image of the source. It could be the sun, it could be the planets, or it could be any other objects. And Doppler graphs, like yesterday what we saw during the heliosismic measurements, we do measure the Doppler velocities of the sun's solar surface, and that we call it as a Doppler graph, which basically measures the Doppler velocities or the line of sight velocities of the object which we are looking at. And vector magnetograph, this also yesterday we had a discussion on how the magnetic fields are measured on the sun using the Michelson Doppler imager (MDI), as well as the heliospheric magnetic imager, using the Michelson interferometer methods. The vector magnetograph, because the magnetic fields are vector in nature, so you need to measure all three axes of the magnetic field measurements. That is the magnetic fields along the line of sight and magnetic fields tangential to the line of sight. Yesterday we discussed only the magnetic fields along the line of sight. Whatever images I showed is only the magnetic field along the sight. Then we do have coronagraphs. Coronagraphs, as again discussed yesterday, that it's an image of the corona by occulting the disk light. Because the coronal intensity is 1 million times fainter, so you have to block the disk intensity to see the coronal intensity. Otherwise, you will not be able to see the coronal intensity. And of course, we also saw a movie of the disturbances propagating in the interplanetary medium from the sun to Earth. That movie also I showed you yesterday. That is measured using the heliospheric images. Heliospheric images are images of the heliosphere, which is the regions between the sun and the planetary medium. Okay, so most of the remote sensing types is mostly for sun, and of course for other objects as well, like planets and moon and etc. And we also discussed about the in-situ measurements. We talked about electrons, protons, and heavier nuclei. So people use the instruments called electrostatic analyzers, which is mostly used for solar wind type of measurements, charged particle and ion spectrometers, magnetometers, and neutral monitors. Neutral monitors is basically looking at the neutral atoms in the interplanetary medium, including the energetic neutral atoms. Energetic means neutral atoms with a very high energy, which is seen during a very high event of solar flares and coronavirus. They are called in situ because it measures the particles in the local environment, and depending on the location where you are, the instrument specifications may vary because the energetic of the particles as well as the magnetic field what you measure would be different at different locations in the interplanetary medium. For example, energy particles inside the Earth's magnetic field will be different from the energy particles what you see it outside of the Earth's magnetic field. The instruments which are marked as bold letters here, like the images and coronagraphs, charged particle and ion spectrometers and magnetometers, are the instruments which are present in Aditya-L1 to carry out both remote sensing as well as in-situ measurements. Okay, why L1? This is an interesting question to ask because L1 is a point which is an important point for the solar astronomers as well as the space weather aspects or the heliophysicist aspects of it. What you see here is the 5 Lagrangian points. Lagrangian points are the points of stable orbits, stable locations where you can have a satellite without expending too much of fuel. You can keep the satellite in the position for a longer period of time. So as you can see, the Sun-Earth Lagrangian points are marked here. The L1 is the point in the Sun-Earth line. L2 is behind the Sun, and L3 is behind. L2 is behind the Earth. L3 is behind the Sun, and L4 and L5 are the adjacent to the solar Sun-Earth line. And typically the distances are the L1 position is roughly about 1% of the distance of the Sun-Earth. Similarly, L2 is roughly 1% of the distance from the Sun-Earth. So they are equal spaced in front of the Sun as in front of the Earth as well as the behind the Earth. And L3, L4, and L5 are in the orbit of the Earth around the Sun. Okay, so that distances of L3, L4, and L5 from the Sun is roughly 1 astronomical unit, which is the distance from the Sun to the Earth. So this is a typical 5 Lagrangian point distances, and Aditya-L1 reached to the Lagrangian point L1 somewhere during the first week of January of 2024, after passing through many Earth orbits and inserted into the L1 orbit. Currently, Aditya-L1 is orbiting around the L1, looking at the Sun. All payloads are looking at the Sun and collecting the data from the Sun. Okay, so I just put together the overall objective of Aditya from the science perspective before we go into the instrument aspects of each of the instrument. Again, I'm coming back to this particular image because this image actually depicts the overall physics which is going on in the interplanetary medium. You have the source, which is the Sun, which is again creating the dynamical events like solar flares and coronal mass ejections, as well as solar wind, and also the particles propagating in the interplanetary medium. So Aditya carries 4 remote sensing payloads to look at the Sun. They are called as VELC, Visible Emission Line Coronagraph, SOOT, Solar Ultraviolet Imaging Telescope, SOLX, Solar Low Energy X-ray Spectrometer, and Helios, which is the high energy L1 orbiting spectrometer. These 4 instruments, through remote sensing measurements, look at the dynamical events on the Sun, such as CME, solar flares, co-rotating interactive regions, as well as the solar wind from the Sun. And Aditya also has 3 in-situ payload, PAPA, particle analyzer package for Aditya, aspects, Aditya solar wind particle experiment, and MAG, which is the magnetometer. So 3 in-situ payloads which looks at the in-situ measurements of particles and magnetic field at the L1 point. So they study those events crossing through the L1 ahead of Earth. So the events which is happening on the sun is captured by these four instruments, which looks at the sun in the remote sensing mode, and the events which are passing through the L1 is captured by these in-situ payloads, looking at both the particles as well as the magnetic field, which most of them will enter into the Earth orbit when it crosses the L1 point. Here is a typical scientific case of Aditya-L1, where we can use all 7 payloads and try to understand the overall energetic events which happens on the sun. Okay, so one of the energetic events which happens on the sun is, we call that as a reconnection. This is a reconnection, as we discussed yesterday about the rubber band system. Assume that you have a rubber band which is connecting the south and north polarity, and what you see here is the magnetic field lines which is connecting the north and south polarity, and at some instance of the time, due to some instabilities, there is a reconnection which is happening at the higher layers. This is as we discussed, one of the case is when the foot points is twisted and turned because of the convective motions. The stress created by these foot points will be seen at the loop top of the magnetic field lines, and when the energy stored exceeds the tension force of the magnetic field lines, this you will start to snap this magnetic field lines, which we call it as a reconnection. What happens during the reconnection is, since the magnetic field lines carries particles, because the magnetic field contains the plasma of the solar gas in the photosphere as well as in the corona. These particles or the gases, what these magnetic field lines are holding it, when the snap happens, the particle gets accelerated in both ways. One is the particle which gets accelerated away from the sun, and if the acceleration energy or the velocity is higher than the escape velocity of the solar gravitational potential, then the particles will escape the sun and travel in the interplanetary medium. And those particles which doesn't have enough energy, or those particles which are accelerated towards the sun due to the snapping of these field lines, they will travel along the magnetic field lines and reaches the lower atmosphere, like the chromosphere and the photosphere. And as the particle travels in the lower atmosphere, as we discussed yesterday, the density of the atmosphere will increase as you go lower and lower in the atmosphere. The density decreases as we move from the photosphere to the corona, whereas here the particle is traveling from the corona to the photosphere. So as it travels along the field lines towards the photosphere, you start to see more and more density. As it starts to see more and more densities, it will start to collide with the local plasma. And because of the collision, the energy gets transferred from the particles to the local plasma, and hence the plasma gets heated up. Okay. So what you would start to see is the particle acceleration during the reconnection. After the particle acceleration, you will start to see enhancement in the brightness in the chromosphere and in the photosphere, depending on the energy of the particles which is traveling. The high energy particles which has sufficient energy will reach the photosphere, crossing all the densities in the chromosphere and reaches to the photosphere. Whereas the low energy particles, which will not have enough energy to cross all the chromospheric density, will lose all its energy at the chromosphere itself. So you will start to see heating of the chromosphere as well as the heating of the photosphere if there is enough energy in the particles which is accelerated down towards the sun. Our current understanding is that this reconnection is the one which is, this mechanism, what I was talking about, the particle acceleration and the heating of the chromospheric and photospheric region, is the one seen as a X-ray emissions during the solar flares. And the particles which are accelerated away from the sun, which is escaping the gravitational potential and traveling in the interplanetary medium, are the particles which constitute the coronagraph detections. So, a single reconnections can explain the solar flares as well as the coronagraph detections. So, this is our current understanding. However, I should point to you that there are CMEs without solar flares. There are solar flares without CMEs. It could mean that the CMEs without solar flare means that most of the particles which are released during the reconnection are above this reconnection points, and hence it all snapped towards the interplanetary medium, and which also has enough energy to escape the gravitational potential. And there are cases where you have solar flares, not CME. That means that the CME doesn't have enough energy to escape the gravitational field, and hence all the particles falls back into the chromosphere and photosphere, and hence you see only the solar flare. So this is one of the theory which is also proposed to have a unified understanding of solar flares and CMEs. Again, I want to tell you that this is only a one scenario case. There are cases where which deviates from what we see in reality. For example, the reconnections do happen in the lower atmosphere, but still we don't see any CMEs. So there are observational cases which it does. Okay, I've also pointed out few examples of the events, the CME flare, which is created by the reconnection or the waves-driven reconnections. This can be addressed by the Coronagraph payload as well as the X-ray payloads jointly observing. And then the electromagnetic radiation arises out in multiband, that is especially when the chromosphere gets heated up and the corona gets heated up, will be seen by the ultraviolet imaging instrument which looks at the chromosphere, as well as the X-ray instrument which looks at the corona. The plasma arises out of it, move away from the site on either direction, which is basically the acceleration of the particles, as well as the plasma motion which happens in the inner corona can be seen by the ultraviolet instrument as well as the X-ray instrument. And the coupling of the inner and outer corona, that is, if you see that the biggest loop is of the order of 1.2 arson. So if you want to study this loop completely, you would need both the Soot instrument as well as the VSC instrument operating together. And of course, all the processes are driven by the magnetic field, and hence you should know the magnetic topology as well as the magnetic field information, which will be given by the VSC instrument. So the remote sensing instrument actually captures the overall picture of the flares and CMEs which happens in the inner corona as well as the chromospheric regions of it. Of course, as the CME propagates in the interplanetary medium, there are other phenomena which happens. For example, the shock, which is seen here in this particular picture, is nothing but the CME interacting with the local ambient solar wind, which has what you call a sound speed, and that CME speed, if it is higher than the sound speed of this solar wind, what you would see is the shock front, which will again enhance the density as well as they accelerate the particles at this particular point of the propagation. Of course, Aditya will not be able to see this particular region. Of course, if you have a good radio observations of this particular region, this can be caught in the interplanetary medium. And at L1, near to the Earth, we have these In-situ instruments, which will capture as the particle passes through it. It will capture the density of the particles, which will start to enhance as it propagates, as you can see. And also, it can also provide you when the shock is propagating at L1, you will see a sudden increase in the density and sudden increase in the temperature. And of course, you also have the magnetic field information, which gives you an indication of that there is a plasma along with the magnetic field which is moving in at the L1 point. I've also included a DST index which is measured on ground at the Earth This basically tells you how the magnetic field of the Earth changes during an event which happens and couples to the Earth's magnetic field. This happens when the BZ component, that is the normal component of the magnetic field, with respect to the Earth's north-south, when it actually increases in the plasma. For example, here the BZ component has increased in this plasma. That will actually couple to the Earth's magnetosphere and start to include a lot of geometric storm at this particular point of time. So a measurement at L1 of all the particles when the shock is propagating, when the magnetic field is in a conducive environment, will indicate to us that there is going to be a geomagnetic storm, which could happen on the Earth side of the process. Okay, so SOOT looks at this chromosphere, and X-ray payloads looks at the corona. And as I said, radio information can give you the soft front, the radio type 1 and type 2 radio bursts. And the particle instruments and magnetic instruments gives you these information at L1, and ground magnetometer can give you the DSP index region. So the gamut of instruments can actually connect from the sun to the Earth in a sequential manner, which provides us an understanding of the space weather aspects of it. Okay, as I said, we have 4 remote sensing instruments and 3 in-situ instruments on Aditya-L1. I am depicting where these instruments are placed. And as you can see, the top deck, this is the top deck where you see this yellow color box is the Coronagraph, visible emission line Coronagraph, built by Indian Institute of Astrophysics. And the green one, which is next to the VSC, next to bigger instrument, is the Solar Ultraviolet Imaging Telescope, which is built by Inter-University Center for Astronomy and Astrophysics in Pune. And there is a mobile tower kind of structure here, which is the one which is hosting the aspects payload, which is built by Physical Research Laboratory of Ahmedabad. It has 2 instruments. One is in the top, one is on the side, and these 2 instruments are mounted orthogonal to each other, so that the top one will look at the particles coming in the ecliptic plane. That means the plane in which the sun, Earth, and the satellite is there, which is the ecliptic plane, and the one which is mounted on the side, which will look at the perpendicular to the ecliptic plane. So you capture the particles coming in the ecliptic plane and the particle coming in the perpendicular to the ecliptic plane. So this is the low energy part of the instruments. We'll talk about the details of the instrument in the later slides. The aspects have more or less like around 8 instruments on board Aditya. What I've shown is here is the 2 instruments, and there are 6 more instruments which are mounted here. So this is the steps instruments of aspects, and there are a few more instruments mounted on behind it. I'll talk about it when we come to it. And the high energy X-ray instrument, which is placed below this top deck, is inside this panel, and you can see this small cutout is the region where the instrument peeks out into the sun, which is built at URL satellite center. The low energy instrument, the SOLX, which is placed below the SOOT instrument, and has a small opening here in front of it to peep the sun through this particular hole. And the Papa instrument is placed in the front panel, which is looking at the sun, and the magnetometer, which is right now in the stored condition, is also placed in the panel which is looking at the sun. So this is the sun direction, where all the instruments are looking towards the sun in this particular mode of operations. Okay. Now let me come to the payloads and their preliminary observations. I start with the SOOT instrument. SOOT is as the name suggests, is an ultraviolet imaging telescope. It images the sun in the ultraviolet band. So it has a 11 filter. So that means it observes in 11 different frequencies or wavelengths. near simultaneously. That means what I mean is it's a single channel. There is only one detector, and the light passing through the filters will select which wavelength you are observing on it. Okay, so it's a single channel instrument suit. It's an imaging instrument. It images the full disk with a reasonably good resolution. And please note that this is the first time in the international community we are doing an imaging in the near ultraviolet band in the full disk mode. Here is the list of filter which is used, the 11 filter which I talked about it, which is used to observe the sun in different filters. And that basically gives you different atmospheric heights. For example, the filter at 214 nanometer with a passband of 5 nanometer gives the image of the photosphere. And the filters, the NB2, NB3, NB4, NB5, these 4 filters gives you an image in the spectral line called magnesium 2 ANH. Magnesium 2 means it's a singly ionized magnesium atom in the chromosphere. And so it looks at the line core of the magnesium in the K and H band, and as well as the wing of the magnesium spectral lines with a very narrow pass band of the order of 0.4 nanometer or 4 angstrom. And we also have filters of 1 nanometer to look at the sunspots. Which of course sunspot is seen in the white light too, as we have shown in the yesterday's talk. But this particular wavelength is important because the sunspots is seen at much higher contrast compared to any other wavelength. So that's where 300 nanometer is used, and 380 nanometer is used to look at the lower photosphere of the region, whereas the 240 gives you a rough mid-level photosphere, whereas 388 will be the lower photosphere. And there's a chromospheric line called calcium lines, and this is a line which is famously observed for the sun over many decades and years. I mean, of course, our own Kodaikanal Observatory has looked at this calcium images for more than 100 years in the full disk mode from the ground-based observation. So we want to continue that in space and give a good context with respect to the ground-based observations. That's why this particular filter is used, and you can see that this is one of the narrowest filter available in suit. And we also have 3 broadband filters chosen at 3 different broadband regions, between 200 to 360 nanometer. They are an important band because these 3 bands gives you emissions in the region which can affect the our ionospheric regions of the Earth as well as the ozone layers in the Earth atmosphere. So these observations from the sun in these 3 bands will give you an energy which is inputted from the sun on our Earth's ionosphere and ozone layer regions. This would be an input to many of these Earth atmospheric modelers to understand the Earth dynamics and how the Earth dynamics, and especially ionosphere and ozone layer, changes because of these input from the sun. And since these inputs are variable, it is an important measurements for us to continuously see these emissions from the sun in these bands. Here is the first light image from the ultraviolet imaging telescope. Of course, you would have seen it on the web. And this is taken in the one of the filters of magnesium 2K, which had a passband of 4 angstrom at 279 nanometer on December 6, 2023. This is taken even before the insertions to the L1 point. And you can start to see the features as we discussed yesterday too. You see the features like the sunspot. What you see is here is a dark patch on the sun. And you would see the plages, which are the bright regions surrounding the sunspot, which is seen only in the chromosphere. So this is a chromospheric image of the sun, what you're seeing in this particular band. And you also see that quiet sun, which is in between these particular regions. So this is a kind of images which you get from the suit instrument on board Aditya. And as I said, suit has 11 filters. You can see a gamut of images taken at different waveband, and you can clearly see that you start to see different features at different wavelengths. And it's interesting to see that, and by looking at these wavelengths, we'll be able to understand the connectivity from the photosphere to the chromosphere by looking at these images from the suit. Please note that these are the images which are not corrected for anything, including the dark and flat field observations. It's a very raw data from the mission. So the correction process and calibration is ongoing currently. We call that as a performance verification phase of this particular mission. And the science ready data will come available only after all the corrections are done and the performance are verified on board. Okay, so I just want to show you some offline structures which we have seen. Of course, you can see as very faint structures which is standing out above the solar chromosphere. We call this as a prominence, and you can see a very nice prominence in this. I have not done any contrast enhancement. If you do a contrast enhancement, you will start to see much better picture of this. And the capability of the suit instrument is that you can choose the field of view too. So, for example, you can see a very narrow, small field of view of a sunspot active regions observed on January 24, 2024. And you can see multiple band which is observed in this small field of view. The advantage of a small field of view is that you start to get higher cadence when you go for a small field of view region. So you can identify a target. For example, here this particular target was identified, and then chosen only that particular region is spread out from the camera on board automatically, and hence the data volume becomes less, as well as since you are dumping all the other regions, you can start to read from the CCDs much faster than reading out the full frame. Okay, I'm going to show a few images or few movies of these observations, just to give you a glimpse of how the dynamics are from these observations. So I'm just going out from the presentation mode for you to show some movies. Let me show the prominences which you saw. You can clearly see that it's highly dynamic. You can see that I'll play it again. You can see that this material is thrown into the interplanetary medium, and then it's subsided. At the end of the movie, you see this prominence no more exists. It is thrown into the interplanetary medium. Okay, some part of it is thrown into the interplanetary medium. Some part of it is going back into the sun itself. Okay, again, as I said, it's not corrected for anything. Once you do an enhancement and do some processing, this would become a much better movie. And I will show you an example of a small field of view observations done on this particular active regions in the issue. And you can see that the brightness do vary as a function of time. Okay, in this particular active regions. Okay. And so this is the particular active region which I showed, and one of this movie, what I showed is this particular active region, how it was dynamically varying. And of course, we have movies of all these other field of view in other wavelength, like what I showed you in the first one. Then coming to the next slide, just give it a minute, it's trying to load. Okay. So this is the first solar flare seen by SUIT, and this happened on December 21st, 2023. I will also play this movie. This is a full disk image, and you notice this particular region where the brightening happens on this particular sunspot. You can see that it brightens very high for about an hour or so, and then goes back to the old intensity. So that's a time where there's a big flare happened in December 31st, 2023. That is the biggest flare happened just before the New Year day. It's a New Year E flare, and that's the biggest flare of 2023 captured by Aditya-L1. Okay, and this flare is captured by multiple instruments on board Aditya-L1. We are currently in processing this particular data to derive some signs out of it from this particular flare. Okay, and again, this particular flare, which is on December 31st, I'll show you a movie on these prominences which erupted. You can see this particular region where the flare happened. You can see the material motion in which throws the material into the interference region. Okay, and if I enhance the color, it is a slow running movie just to show you that there is an eruption which happens, and the eruption throws the material into the interplanetary medium, and you can see the accelerated part of the loop and the king structure, which is typically seen in the coronal mass ejection. So this flare also had a coronal mass ejection happen, and so this suit instrument has caught this the flare as well as the CME, which is propagating in the. So we will be able to continuously see this eruptions in both in ultraviolet as well as in the X-ray payloads. So let me talk about the X-ray payload. Since I started off with X-ray flares, I thought I'll go into the X-ray payload. SOLX, which is the low energy X-ray spectrometer, it's sun star spectrometer. Observe the photons from 1 to 22 keV, and their aperture door was opened on 13th of December 2023. And we were lucky enough that as soon as we opened the door on 13th, and the 14th and 15th, we had a lot of activity which happened. So what you see here is a light curve, that means the flux, the counts from the SOLX instrument, how it varied as a function of time. You can see that the flux has a kind of a variability at the different time scales as well as the different flux scales, and they're related to the class of the flare. For example, this one where I have marked it, it's an X2.9 class flare, close to X3. So this is X1, X2, and X3 kind of flares, which happened on the 14th of December 2023. And you can also see M class flares, which is in this M1 to M10 region. So a couple of M class flares also seen, along with the multitude of C class flares which were seen here and there. So on a single day itself, SOLX started capturing many flares from it. And this is also compared with the GOES instrument, which is also looking at the sun for the flares. And you can see that both matches pretty close to each other. The difference between SOLX and GOES is GOES doesn't give you a spectroscopy information, whereas SOLX gives you the spectral information in this energy band, which is an important information for you to extract the physical parameters of this plasma in the coronal regions of the flaring. Okay. Here is an example of the spectra, what you see from between 3 to 15 keV energy band. And what you see here is the two instruments. One is SOLX, another is XSM, which is on Chandra-N2, which is also capturing these X-ray flares. And you can see that both instruments shows one-to-one matching of these particular flares once we take care of the area ratios between the two instruments. And here is the light curve of that particular flare from these three instruments. And so it clearly shows that we are able to capture this flares along with its spectral information. And you can see that some of these bumps, what you are seeing here, are basically the emission lines, which is seen in the X-ray band, and which tells us about the temperature of the particular region, as well as the abundances of these species in the corona. So SOLX will be able to give you the temperature, the emission measure, that means the brightness of the corona, as well as the elemental abundances of these elements like iron, nickel, calcium, silicon, sulfur, argon. So all these elements can be seen in the coronal as during the flare evolution process. Here is an example of the derived parameters. For example, emission measure and temperature. What you see here is the light curve from the GOES, and the green one is the estimated temperature from the GOES with a very coarse spectral information, whereas the estimated temperature of the SOLX with a very high spectral resolution. You can see that the GOES underestimates the temperature as well as and overestimates the emission spectrum. So it's an important information, which of course we know it from previous observations. And here you have a case study for the elemental abundance variations during a flare. You can see that the elemental abundances do vary during the course of the flare. So SOLX will be able to address many of these elemental variations during the flaring conditions. The Helios instrument, which is the high energy part of it, going from 8 keV to 200 keV. We'll also look at the solar flares. Here is an example comparison of the same flare which happened on December 14th. The light curve from the SOLX, which is given in blue, and the light curve from GOES, which is given in the red curve in this energy band, and the light curves provided by Helios in the energy band of 6 to 30 and 30 to 150 keV. You can clearly see that the photons which are emitted during this particular flare can reach up to about 150 keV during the peak of the flares and during the decay phase of the flare. So there are very high energy accelerated particles which are seen in this particular flare, and this flare is being studied in more details, because you can start to see that there is a lot of interesting particle acceleration happens during the peak of the flaring event, which is an indication of multiple flares, multiple reconnections which is happening during this flaring process. So that's why you start to see not only one peak, you start to see multitude of peaks even during the decay phase of the flare. Here is an example of recent flare, February 22, 2014. So this is the biggest flare of this year, 2024. Happened on February 2022. And here also we started to see that the energies reaching up to 125 to 150 kV, the highest energies which are seen in this particular flare too. So SOLX and Helios together will start talking about the particle acceleration and the heating mechanism. And the suit will tell you about the chromospheric activities and chromospheric brightness to these flares. So that gives you the connectivity which I talked about in the beginning. And let's come to the in-situ payloads. As I told you, the aspects had two set of instruments. One is called Swiss solar wind ion spectrometer. Another is STEPS suprathermal and energetic particle spectrometer. Operates in this particular energy range, 100 keV to 20 keV and 20 keV to 5 MeV per nucleon. And they are mounted like this. So the tower-like structure, you had the Swiss 1 and Swiss 2 mounted perpendicular to each other to measure the particles in the eclectic plane and perpendicular to the eclectic plane. And as I told you that we also have this STEPS instrument mounted here as well as mounted here. Mounted here as well as mounted on the back side of the satellite. For example, here you can see that STEPS 2A and STEPS 2B, and STEPS 1 is mounted in the front. And the processing electronics are mounted inside the deck for all the instruments to get processed. The uniqueness of this is it does a multi-directional measurements. That means the particles coming from multiple directions along the ecliptic plane and perpendicular to the ecliptic plane is observed. And it also gives you the hydrogen and helium measurements. That is the alpha and proton ratios, which gives an indication of when the CME shock arrives at the L1, because the shock region gives you an enhanced helium compared to the hydrogen. So you will be able to predict when the shock is reaching again. Here is an example of the 15th to 19th December 2023. Again, the flare and the CME, which is shown on 14th of December, reached L1 on in this duration, 15 to 19 duration. You can start to see that there's a lot of activity happening from middle of December 15th all the way up to December 19th. Okay, this is from Swiss 1 instrument, which is along the ecliptic, and this is from Swiss 2, which is perpendicular. Here is a comparison of the Swiss measurements with the wind measurements of NASA's satellite. You can see that both capture the event very well, but one of the advantages what we have is compared to the NASA instrument is that the NASA instrument picks up only the events crossing above a certain threshold. So you can see that these regions, you don't see any particle counts because they don't count these particular regions, these energy windows. They count, they have a logic which counts only the particles crossing certain thresholds. Whereas aspect gives you all kinds of particles, even the very high energy particles, which is missed by the wind instrument, is caught by the aspects instrument on the Here is the same measurements from the STEPS instrument. STEPS looks at the hydrogen and helium as a function of time, and you can see that the 5 instruments, 5 detectors which are kept at different locations, different orientations, measures these particles as it varies. You can see that there is a shock arrival at this particular time for all the instrument which shows it, and you can see that a lot of dynamics happened between the 15th to 19th of December 2023. Coming to Papa instrument was switched on 11th of December. It again looks at the electrons and ion species, while aspects of looking at the proton and ion, Papa looks at the electrons and ion species. And here is an example of the December 15th event, again in Papa. You can see the shock arrival somewhere around middle of December as captured by the aspects 2. And here you can see that Papa also has 2 instruments, sweep and Swika. While the sweep looks at the electron, Swika looks at the ion part of the solar wind. You can see that both of them capturing the events very well and well correlated with the magnetic field measurements from the NOVA instruments, which is already operating. Here is the February 10 to 11 event captured by Papa instruments of sweep and Swika instrument. And here is the directional information. The hydrogen and helium is well separated in the spectral channels. And here also it gives you the directional information of that particular event and from which direction it is coming from in terms of the degree angle from the sun. Then coming to magnetometer, it was switched on in October 16, though in the stowed condition. So whatever the measurements which I'm going to show is in the stowed condition. One of the disadvantages of the stowed condition is that the satellite current changes will also induce a magnetic field on the instrument. So this will be a combination of the local magnetic field which presents in the in-situ, as well as the magnetic field generated by the spacecraft. When the boom is deployed, which was deployed after January 16th, somewhere around January 10th or 11th, it was deployed. The satellite magnetic field is not sensed by this instrument, or it's sensed the satellite magnetic field will be much lower because it is much away from the satellite body. Whereas the in-situ magnetic field, it will be sensed by in-situ magnetic field with much higher accuracies. Since magnetic field is a vector quantity, you will have a 3-axis measurements. So we'll have Vx, Vy, and Vz. And we also compared with one of the discovered spacecraft, which is Aditya-L1 by the NASA mission. And you can see that both do measure the Vx component pretty close to each other, except for durations where you see a enhanced Aditya signal, which was attributed to the spacecraft operations which happened during this particular time. This is Bx, this is By, and this is Bz component from the three from the three sensors which is mounted on the deployable board. And the big instrument, visible emission line coronagraph, all four channels. It has a 4-channel, one continuum channel, and 3 spectroscopic channels. All 4 channel detectors are switched on. Health is normal. The entrance door was also open. However, we are in the process of putting the disk light into the occulted portions for us to look at the corona. So far, we are in the operation of putting the disk light into the in the center of the occulted position. So we are yet to get a good coronal images from this instrument so far. However, I am going to show you some spectroscopic informations which can be, the performance can be evaluated from the disk images, which is obtained when the sun is not fully affected. What you can see here is the kind of a crescent sun, which is seen. This is the occulted portion of the coronagraph, and this is a crescent sign which is peeking out of the occultation. And the slit of the spectrograph is mounted in this configuration. So you get the spectral informations from the other 2 spectroscopic channel, the spectral details of the regions where the sunlights are visible. So you can see that the disk spectra, the absorption features, which is also identified with the wavelength in this particular region. And so this is you can see that this is 5302.3 and 5300.58, and our coronal line will come at around 5303, which is in the center of the pastime. So this is where we would be expecting a coronal emission line when we center the sun in the occulted portion. Here is an example of the close occultation, which happens when the sun is almost going to into the occulted region of the DSC. There is still some sunlight which is peeking out. Currently, we are in optimizing the position of the satellite as well as making it more stable, so that as the sun is put into the occulted region, we'll start to see the coronal signatures in the coronal. Okay, before I wind up, just have a few things to say. One is Aditya-L1 is unique with respect to many other missions flown so far by the international community, or many other missions which is going to be flown in the future. So these are the 7 points which I listed out as the achievements of Aditya, and the points which are marked in color are already established by our initial phase of operation. The points which are in black is yet to be established, and we are on the way to ensuring that the uniqueness of Aditya-L1 is meeting the required science objectives. So some of them are, we want to look at the coronal mass ejections dynamics closer to the disk, which is not done by any other mission so far. The coronal magnetic field and topology of active regions from space. This will be the first time we'll be doing it from space. The spatially resolved solar disk observations in the near UV. As I told you, so far, no other instruments flown which captures the full disk in this particular near UV band. Of course, there are narrow field of view instruments which were flown by other countries, but none is done has the full disk results. And we also have onboard intelligence to detect CMEs and flares for optimized observations and data volume, so that we can go into very high cadence observations when the CMEs and flares are detected on board. The logic is yet to be studied, though we have observed a lot of flares. The logic is yet to be finalized and optimized for us to go into the regular phase of operations with the trigger enabled. Flare observations, as I told you, I should show you a lot of flares will be observed without any break or sensitivity change. And we also observe the solar wind electrons, photons, and alpha particles with the direction information from the aspects and papa payload. And we also have identified flags which comes to ground much earlier than the actual data comes in the spacecraft. These flags can be utilized for early warnings or early indications of what kind of events which has happened on the sun much before the actual data comes to the ground. So this flag is being established on ground for us to give an early information on the space weather events, which is seen by Aditya-L1. Before I close, I just also want to let you know that we have a support cell, which is a handshake between the users, like many of you guys who want to use the Aditya-L1 data, and the Aditya-L1 team here at ISRO, as well as the payload teams from different institutes. The support cell is the handhold between the payload teams as well as the users like you people. They do conduct trainings for the users of Aditya-L1 and the payload and science team of Aditya-L1. Okay, they do have a lot of training programs for users with the Aditya-L1 proposal processing system, because Aditya-L1, if any of you are interested, you can even propose your own observation sequence when it is open to the public. We also have simulated data, so to train you guys, and they also train you from other missions, which gives you a complementary data along with Aditya. And they are the focal point for clarifications and any queries from users related to the proposal submission form, which will be opened up for the users once it goes into the science commission phase mode of the mission. And they also do science support for the payload proposal processing system in close collaboration with POCs. And they also will provide higher level data products, which is not generated by the payload teams, so that the users can utilize these higher level data products straight away to do their science than they themselves start doing it. And the users can contact them for any other specific support required, which are relevant for general science outcome of Aditya-L1, but not in the scope of payload operations centers or the payload teams. Okay, I just want to let you know that this coming May, there is a workshop which will be conducted at IIRS Nainital. So you just go and search in the internet on Aditya-L1 support cell. Keep watch on this particular web page. As and when the workshop gets on the web page, you'll be able to apply if you are interested. And this is a 10 days workshop where they cover all the aspects of solar physics as well as the data processing. And this may be the first workshop where we will actually bring in actual Aditya-L1 data and start training you to utilize the data for future scope and future science from many of you guys. So with that, I think I'll stop here and hand over to IIRS for the questions and any discussions. Thank you all.